Cool. All right, so that's what a buffer is. It's a mix of a weak acid and its conjugate base, or a weak base and its conjugate acid. And why do we use buffers? Because buffers are resistant to pH changes. All right. So just to take a step back, I remember first learning about buffers and really not appreciating why the heck we bothered using them. All right. So sort of just to take a step back and to contextualize why they're so important in chemistry. If we, let me mute. Cool. Let's think about like the inside of a cell. Okay. Inside of a cell, there's all these sort of working machines that are going on, right? These things we call enzyme, and this isn't a biochemistry course, so we don't really need to know the terminology. But we think about the inside of a cell kind of like this giant factory. And over here in this corner, you have the machines that are breaking down the sugars. And over here in this corner, you have the machine that is assembling the proteins, et cetera, right? There's all these functions being carried out by little machines in the cell. Well, it turns out that all these machines will only operate at a very specific pH. If the pH of the cell gets disturbed, they're in trouble. Those machines break down. All right. So the cell employs buffer systems. They make these buffers in order to make it so that the pH is constant at all times. So why would that be important? Well, what do we all know about the mitochondria, right? The mitochondria is the powerhouse of the cell, right? Hopefully we got that ingrained into our brain from a high school science class. All right, and what does that really mean? The mitochondria is where ATP is made. ATP is like the energy currency, the machine that breaks apart the sugar. It needs ATP to fuel that action. The machine that's making the protein, it needs ATP to carry out that function, right? So that's what the mitochondria is doing, is it's cranking out ATP. ATP is super acidic. Okay, if you take ATP and you drop it into water, the pH will crash down because it is a very acidic compound. Well, the cell can't have that. The cell can't have the pH crashing as it's making this ATP, and that's why it uses those buffer systems, right? So that as ATP is being made, the pH of that cell isn't going to change. All right, so that's why buffers exist. They're very important because they make it so that if you add a little bit of something or take a little bit of something away that would change the pH remains relatively undisturbed. That's not to say that it doesn't change at all, but it's resistant to change. It changes very little compared to if there was no buffer there at all. All right, so first thing we're going to do is we're going to take a look at a buffer system here. So we're going to have HF, which is a weak acid, and we're going to put that into water. And based on what we did last week, you're going to take a second and tell me what the conjugate acid and conjugate base are. What are the products of this reaction? All right, and hopefully I have it cemented in your brain here. What do acids do? They donate protons. So my conjugate base is going to be the fluoride ion. And what do bases do? They accept protons, and that's how I get my hydronium ion concentration. All right, so now so we got our balanced chemical equation. We said that's step one. And step two is you're going to build me that Ka expression. All right, and remember, what do we remember about our equilibrium constants? Products over reactants. Every time I'm building a equilibrium constant, that's what I'm chanting over to myself in my head. I'm going to take the products of this reaction put it over my reactants. Again, we're not going to include water because it's a pure substance. There's so much of it that the concentration will not change. Okay. Now, in order to get the Ka for this reaction, we can turn to one of our constants pages, right? So this is going to be one of the things that you have on the exam, is going to be a constants page, which lists the acid-base dissociation constants for all these different compounds. I want to change the view. There we go. So what I'm going to do is I'm going to look it up for HF, for hydrofluoric acid, and I get my 6.8 times 10 to the negative 4. All right, so this is going to be one of these tools that we need to be able to use, are these charts that contain this information that's relative, right? That's a big part about being a scientist, is knowing where to go and what to look up for a particular problem, right? So if we're dealing with a weak acid or a weak base, we need to look up its Ka or its Kb value. So 6.8 times 10 to the negative 4 is what we're going to use. All right, so this is my 6.8 times 10 to the negative 4. Now, previously, what we had done were problems where you could determine the pH of a solution starting out with this initial concentration of HF, okay? But now we have a buffer solution. So my initial concentration, I'm going to have both some acid, some weak acid in there. We'll say that the initial concentration here is the 0.100 molar. But we also have, hold on, let me mute. We also have some of our conjugate base present as well when we start out, right? So now when I start out, I don't just have only weak acid, I also start out with my initial concentration of my conjugate base. All right, so now when I'm building my ice table, and I'm keeping track of the concentration of all these different things, my reactants and my two products. All right, so now, not only am I going to have an initial concentration of that weak acid, but I'm also going to have an initial concentration of my conjugate base, right? I don't have any of my hydronium ion, because the way that this solution was prepared was you actually took some hydrofluoric acid and some fluoride ions and mixed them together to create your solution, right? So initially, these are my two concentrations, even before any reaction has occurred. Now what's going to happen is, again, I'm going to be consuming my reactants, and I'm going to get the same amount of product that's produced. But now my change at equilibrium, I'm going to sum up my I and my C boxes. And so we see the big difference is what happens in this box right here, right? No longer is it just X, but it's that initial concentration plus the value of X. All right, so then we're going to turn around and plug this into our expression for Ka. Remember, that's why we create our ice table, so that we know what to plug in up here. That would be that value there. My fluoride ion concentration, that's that value there. I guess it's an expression, not a value, but yes. And X will go for my hydronium concentration. Okay. And before I plug these in, I'm going to actually, let me make some more room. So I'm going to take this stuff and take it to a new page. Before I do that, I'm going to rearrange this Ka expression to solve for this value here, right? So I'm going to put that all by itself and the Ka on the other side, right? So this would look, if I rearrange this expression, I'm going to get my hydronium ions all by itself. And that's going to be equal to Ka times HF over F minus. Okay. If I plug in my values here, X was the hydronium ion concentration. I got my Ka. And then for my ratio here of acid to conjugate base, right? That's what my expression has become when I rearranged it. Okay. And because X is going to be so small, we're again going to be able to make this assumption where these values, we're just going to say that 0.1 minus X, well, that's basically 0.1. And 0.1 plus X, that's basically 0.1. Right? So again, make that simplifying an assumption, and that will just make our algebra easy. It's not like you have to make that assumption in order to solve the problem. It just makes your algebra a lot easier. All right. But then what we're going to do is, and we're sort of trying to build what's called the Henderson-Hasselbach equation here, is we're going to take the negative log of both sides of this equation. Okay. And the algebra for logs is kind of its own thing, and I don't want to get too bogged down in explaining it. So I'm more than happy to explain it to you if you want to hang out afterwards. But in terms of like the details of deriving this equation, I think most people are going to be comfortable just trusting me on this. So first of all, what's the negative log of X? What's the negative log of that hydronium ion concentration? We have a special name for that. Everybody in the chat, real quick, what would that be? What is the negative log of the hydronium ion concentration? Exactly. So pH. This is going to be equal to now the negative log of the Ka, which is what we call the pKa, plus, and this is where the algebra of logs get a little weird. Multiplication, when you put it on a log scale, becomes addition. And if I take the log, the inverse is its negative. So again, you can just trust me on this, that this is going to be the concentration of the base, which is in this case, the fluoride over the acid, the fluoride ion over the acid. And this is what we call the Henderson-Hasselbach equation. Okay, you see that I've got it from my ICE table, and I want to make something kind of clear here. You can always use an ICE table to solve these problems. That's like the standard way. We have these things. So for example, again, this was called the Henderson-Hasselbach equation. And we sort of have them because they make our lives a little bit simpler if we know the context in which we're supposed to use it. And importantly, when you think Henderson-Hasselbach, you think buffer. That's the only time you should be using your Henderson-Hasselbach equation, is when you have a buffered solution. Okay, so if you know when to use it, and again, that's when we're talking about buffers, it can make your life a little bit easier. But again, the ICE table is always the correct way to do it. That's kind of like the standard one-size-fits-all way to approach all of these equilibrium-based problems. Okay, so I want everybody to take a second, and we're going to play with this function real quick. All right, so first of all, we said that the pH is equal to the pKa plus the log of the concentration of base over the concentration of acid. I want everybody to take a second and tell me what my pKa is, right? For this particular reaction, we said that the Ka was 6.8 times 10 to the negative 4. So everybody take a second and tell me what the pKa of this reaction is. Let's use the chat. What do we get? Yeah, and be careful. Some of y'all are chopping it off instead of rounding it. So if you're going to round it off to 2 decimal places, it's not going to be 3.16 unless I punch this into my calculator wrong. Right? That will round up to 3.17. Okay. So I like to keep a bunch of digits and then keep my sig fig marked. All right. So what I'm going to do is just say, actually, we can make our lives a little bit easier. Let me, again, these problems require too much paper. So my pKa here is this 3.17. We'll just keep it simple numbers to make a point here. All right. Now, we said that our concentration of base of conjugate acid and of acid and conjugate base were both 0.1 at the beginning of this reaction. So I want everybody to take a second and take the log of that ratio right there and tell me what just this value is here. So again, this is 3.17. What value is the log? Well, so first of all, 0.1 divided by 1, right? This is the same thing as the log of 1. Let's just take a second and figure out what the log of 1 is real quick. Exactly, right? So if these two are equal, if the acid and the conjugate base concentrations are the same, well, the log of 1 is 0. So that means that the pH equals that pKa, right? So pH equals pKa if the concentration of the conjugate base is equal to the concentration of conjugate acid. Okay. All right, now let's say that instead we're going to just play with this ratio here again. Let's say that we have 10 times as much acid let's say that we have 10 times as much acid as we do base. So what's that going to look like is this 3.17 plus the log of 1/10, right? 10 times as much acid as we have base. So actually, everybody take a second and just tell me what that log portion is. Right, so this will decrease the pH by 1 unit, right? So compared to my pKa, if I did this, I would have 2.17. And that makes sense, right? Whoops. More acid. That means my pH is decreased. And again, by 1 unit, right? 1 pH unit. So now let's do the exact opposite. So this was 10 times more acid. Now we're going to do 10 times more base. Okay. So we're going to take our pKa and add the log of, now we'll say 10 times as much base as acid. All right. And again, what is just this portion here? The log of 10/1. All right. So now we're increasing this by 1 unit. Right, 1 pH unit. So this would be 4.17. Okay, which again, hopefully makes sense. More of the base means that we have a higher pH. All right, and this is what we call the effective buffer range. Outside of this buffer range, right? So again, effective buffer range. That is pKa when the pH is the pKa plus or minus 1 unit, right? That's the effective buffer range of a buffer. Or when there's a 10-to-1 ratio of acid to base or base to acid. Okay, this is what we call the effective buffer range. It turns out that buffers do not really work outside of this range, right? A buffer cannot buffer against pH changes if the pH is more or less than 1 unit away from its pKa. Or another way of saying it is that there's more than 10 times as much acid than there is base, or more than 10 times as much base as there is acid. This right here is the effective buffer range. And again, we just showed that these two were saying the same thing. But yeah, so that's what we call the effective buffer range. Buffers can do very well at preventing pH changes around their pKa's, but they can't when the pH is either too far or too less. And so, in fact, the optimal buffer is when the pH equals the pKa, or there's a 1-to-1 ratio of acid to base, right? That's when a buffer is doing its best job at preventing pH changes, is when the pH is equal to the pKa, which is, again, the same thing as saying there's a 1-to-1 ratio of acid to base. All right, so then let's sort of dive in on some of these questions that we have from our worksheet here. I want you guys to take a few minutes to try to answer these first 4 here. We shouldn't really need to do any math, just to be thinking deeply about what it is that we just learned here. So everybody take a minute and answer these 4, and then we'll sort of do a iClicker poll of a few of them and see how well we do here. All right, so I'm going to open it up for question 1 here. All right, so right now you're going to take a second and use our iClicker to tell me whether you think A, B, C, D, or E is correct here for this first question. Which of the following statements about buffers is true? All right. So for this one, the correct answer is B. A buffer resists pH change by neutralizing acids or bases, okay? Importantly, A and C are kind of saying the same thing, that it does not change the pH. I'm sorry, A and D, or that a buffer can absorb an unlimited amount of acid or base. That's not true. The pH does change a little bit. It's just resistant to that pH change. So it doesn't change nearly as much as it would as if you had a sample of pure water. And we're going to illustrate this mathematically when we talk about titrations on Wednesday. Okay, but it's not that it can absorb an unlimited amount, and it's not that the pH doesn't change at all. It's that it's resistant to change. It changes much less than it would without that buffer there. Okay, but absolutely, when you're adding acids or bases, they're just going to react with your conjugate acids and conjugate bases, or I'm sorry, your acid or your conjugate base. And so that's how this reaction is resisting pH change. Okay, number B, let's do two together here. So which solution would be a good buffering system? So remember, we need acid and its conjugate base. A has a weak acid, and I guess actually let me put that, weak acid and its conjugate base. A has a weak acid, and it has a conjugate base, but it's not this weak acid's conjugate base, so it's not going to be that one. HCl, strong acid, so get that one out of here. Likewise, D, NaOH, KOH, those are strong bases, so those aren't going to count here. But on C, we have a weak acid and its conjugate base. So C would be the correct answer for which of these solutions is a good buffer solution. Okay. All right, let's open the poll up again. We're going to do problem 3 here. So everybody take a minute and submit what you think would be true. If the pKa is 3.74 and the pH of this solution is 3.11, which of the following is going to be true? Okay. So if we look at our Henderson-Hasselbach equation here, I'll give you a few more seconds here. All right, if we look at our Henderson-Hasselbach equation, this says that the log, or rather the pH is equal to the pKa plus the log of base divided by acid. If these two are equal to one another, as they are in C, well, then this value here is going to be 0. So that would mean for C, this is when the pH equals the pKa. But if we look at our problem here, my pKa is 3.74, but the pH of the solution is 3.11. So it's less than that pKa, okay? And what we sort of showed this plugging in numbers here, we can see that if the acid is greater than the base, as is the situation here, that's when the pH is going to be less than the pKa. Right? And so hopefully that makes sense. More acid means a lower pH, right? So this would be the pH less than the pKa. If we have more base than acid, it's going to be the opposite. This is when the pH would be greater than the pKa. Okay, so again, going back to that Henderson-Hasselbach equation, the only time that the pH is going to equal the pKa is if those two concentrations are exactly equal. Okay. And then the last one, let's do this one. Let's see who was paying attention here because we went over this explicitly. So which of the following is true? A buffer is most resistant to pH changes when the concentration of acid equals the conjugate base. A buffer cannot be destroyed by adding too much strong base, only by adding too much acid. The effective buffer has a base to acid ratio of a range of 10 to 100. And the effective buffer has a very small absolute concentration of acid and conjugate base. All right, so a buffer does the best job at being a buffer when the concentration of acid is equal to the concentration of conjugate base. All right. You can absolutely ruin a buffer by adding too much strong base, just like you can ruin it by adding too much strong acid, right? It's resistant to this pH change, but as soon as it's outside of that effective range of plus or minus 1 to the pKa, it's not going to do its job of being a buffer anymore. Okay, and we talked about this effective ratio, but the range that we talked about was 10 over 1 and 1 over 10, right? To where the ratio of acid to base at 10 times more acid than you have base, or 10 times more base than you have acid. So this would be an effective range of 0.1 to 10. That's my effective range, which again, we said was the same thing as pKa plus or minus 1 unit. Okay. And for this last one, it says that it's most effective when you have a small concentration of acid or conjugate base. It's actually the opposite that's true. So the larger the buffer concentration, the better it is at being a buffer, at resisting pH changes. All right, so now let's look at these things, these last few ones where we look at things mathematically. So actually, we don't have to do any math for this first one here. So everybody, let's take a second. Which of the following acids with their pKa values listed would be the best at being a buffer for a pH of 8.10? Let's try to do this one quick so we don't run out of time here. Okay, remember the rule, pKa plus or minus 1 unit. So there's only one up here that would satisfy that rule. If my pH is 8.10, I would have to use this one here because that's the only one where that pH is within plus or minus 1 unit of the pKa. All right, so now we wish to prepare a buffer with a pH of 4.24. If the pKa is 4.74, what's the ratio of base to acid that we want to use? So let's look at our formula. pH equals pKa plus the log of base over acid. Right, and that's what it wants to know, is this value right here. Well, if we just rearrange, we have the pH minus the pKa equals the log of that ratio that we care about, base over acid. right? And that difference, if I take my pH and I subtract my pKa, would be negative 0.5. So, I mean, to be honest, there's a few ways that we could do this. One is just kind of trial and error, because this is a multiple choice problem, right? Let me just plug in these values, take the log of them, and see what matches. Or we could be, if we remember our algebra, we could be good and do the inverse of a log function, which would be to take 10 to the negative 0.5, and that will equal that ratio of base to acid. Remember that these are inverse of one another. Taking the log of the inverse function is taking 10 to the power of that thing. Right, so if we did this, this would give us a base to acid ratio of 0.32. All right. So now I want everybody to take a second and do problem 7. And I'm going to open up the iClicker to see if we can all get the right answer here. All right, and since this is a buffered solution, we can use Henderson-Hasselbach's equation. Oh, not equals, plus. All right, so the easiest way to do this problem is to notice that my conjugate acid, or my acid and my conjugate base concentrations are identical. So this is the situation where pH is just going to equal the pKa, the negative log of that Ka. Right? So if we take that and we punch it into our calculator, we get this 3.46 value here. Right? So you could have also plugged those concentrations in and you would have gotten the same value. But again, because the concentration of conjugate base is equal to that of the acid, the pH is just going to equal the pKa. All right. So now for this next one here, this is the last one we're going to have time for. Although it's incredibly similar to the one below it. So I'm confident if we can do 8, we can do 9 as well. All right, so let's look at this. Calculate the pH of a solution formed by mixing 100.0 milliliters of 0.2 molar chloric acid with 200 milliliters of 0.03 molar potassium chlorate. I guess how we'd say that. All right. Now, what key piece of information is missing from this problem that's going to be preventing me from being able to solve it? Let's see who can get it in the chat here. Absolutely. We're not going to be able to solve this problem unless we have the equilibrium constant for this acid dissociation because it's a weak acid. But remember, how can we find that? We can just go to our pKa chart, right? So again, being able to use the tools that we are given. Oh, I was wrong. It's not caloric. It's hypochlorous. Is going to be very important here. Oops, I called the acid the wrong name. My bad. 2.9 times 10 to the negative 8 is going to be our Ka that we're going to use. All right, so here we're just going to say that our Ka is that 2.9 times 10 to the negative 8. Okay, now the other thing about this problem that's going to be tricky is that you mixed these two solutions together. So although you have the initial volume and the initial concentration, the concentration is going to be different after you mix them. But the good news is that since the volume is going to be the same once you combine these, we can actually sort of simplify things. If we take our Henderson-Hasselbach concentration of base over acid, you could absolutely just take a minute and figure out what your new concentration is. Or since the volume is going to be the same, we can actually just take the log of moles of base over moles of acid, right? Because at the end, we're going to divide those two by that same volume because they're mixed together. They've created one solution. All right, so everybody take a second and finish off this last one for me. Again, if you need to go, that's cool, because I understand I'm not doing great at keeping this 15-minute time limit. Nonetheless, I'll keep it going and solve this last problem, and you can look at it when the video is posted. All right, but everybody take a minute, and we'll just use the chat for this one. A, B, C, D, or E. Tell me what we think our final our final pH is going to be. I'm going to get rid of this just to make some more room for myself. All right, so remember, big M stands for moles per liter, right? So that means volume, if I take my volume times the molarity, liters times moles over liters, that volume cancels out, and so I'm left with moles. All right, that's how I'm going to get to moles of acid and moles of base. Volume times concentration will give me moles. And actually, I'm given the volume in milliliters. Of course, I can convert to liters and get to moles. That's fine. If I leave it in milliliters, what's going to happen is those liters still cancel out, and I'm left with, but the milli doesn't. And so I'm actually going to be left with millimoles. And that's perfectly fine as well. Anything that you can do in moles, you can do in millimoles as well. Okay, so either one of those would have been fine, but that's how I'm going to have to calculate the concentration of base, or rather the moles of base and the moles of acid. All right, so I'm going to take my formula. Oops. pH equals that pKa. And I'm going to add now the log of moles of base. So up at the top, I'm going to put in parentheses my base. And remember, this is, I think, maybe the easiest place to get tripped up here. The base is this thing here. All right, this is my acid. So my base would be the 200.0 milliliters times my 0.30 moles per liter. So that value would then be in millimoles. And now I'm going to take my 100 mils, multiply that by the 0.20 molar. That would give me my acid in millimoles. So I can punch this into my calculator. I guess just to be good, the pKa is the negative log of that 2.9 times 10 to the negative 8. All right, so I'll substitute that in. Whoops, should have known that that was going to happen. All right, so this is so I punch that into my calculator and I get that my pH is going to be equal to 8.01. All right, and again, I found that by getting my moles of base divided by moles of acid, right? Because the volume changed when I combined these things. Again, you could have just taken a second to recalculate the base and the acid concentration, but you would have been essentially getting to moles anyway. So why not stop there and make your life easy? All right, and I'll do this last one again. If you need to go, that's fine, but just to have it on the video. Okay. I didn't give you this piece of information. All right, so now I want the pH formed when a 250 milliliter solution of 0.15 molar ammonium chloride is mixed with a 200 milliliter solution of 0.12 molar ammonia. And again, this is going to be a buffered solution. So I'm going to be looking to fill in my equation pH equals pKa plus the log of the concentration of base over acid. Again, I need that equilibrium constant, but here it's not going to be listed for the acid. It's going to be listed for its conjugate for the base ammonia. So when I go to my table here, right, ammonium chloride isn't what's listed. It's going to be the base ammonia. And that gives me the Kb, 1.76 times 10 to the negative 5. So here my Kb is given. But remember, we have this relationship between Ka and Kb. If I know the base dissociation constant, I can also figure out what it is for the conjugate acid, right? So my Ka times the Kb is equal to that 10 to the negative 14. So I'm going to do is just solve for my Ka, take that 10 to the negative 14 and divide it by 1.76, not 5, times 10 to the negative 5. And that will give me my new Kb value. I'm just going to take a bunch of digits here. We don't like punching rounded numbers into our calculator. It's 10 to the negative 10. All right. And then the other trick of this problem is, again, going to be to note that my base and acid concentration are going to be different after I mix these two things. right? Here's my initial acid concentration, but it's going to change as soon as I mix them. So again, what I'm going to do is, since they're going to be at the same final volume, I'm just going to use this equation, but talk in terms of moles. Okay, so pH is going to be equal to the negative log of that 5.68182 business. I'll keep my sig fig marked to be good, plus the log of the concentration of base over acid. But instead, since they both are at the same final volume, I'm going to do moles of base over moles of acid. I'm going to do it the same way we did our last problem, where I take volume times concentration. Actually, we'll make it millimoles just to make our lives easier, save us a conversion. So my base is the 200.0 mLs times the 0.12 molar divided by my acid, which is 250.0 mLs times the 0.15 molar. All right, and so my final answer that I get here for my pH is the 9.05169. We're being good about sig figs. I kind of neglected that in the last problem, but I have 2 in my concentration, so that would mean 2 decimal places. The correct answer is B. Truthfully, in this problem, the value that was given, they gave you the Ka on the worksheet, or the KB rather, and it had one fewer decimal place than our table did. We always want to use the more decimal places as well, but that's why the answer is slightly different, 9.05. All right, but that's how we calculate pHs of buffered solutions. And again, buffered solutions are when you have a mixture of acid and its conjugate base, or weak base and its conjugate acid. Okay, and so what we'll see next time is to do these titrations where we start adding acid or base, and we're going to indeed see that we're resistant to pH changes in our buffered solutions.